Morning, everyone. How y'all doing? Happy Monday. Anyone have any questions, concerns, needs, etc. before we get started today?
I do have one question.
Okay.
I just heard somebody say that each year all the planets get closer to the sun. Is that true?
It's possible. I haven't looked into it specifically, but it's possible and even probable, if I'm being honest. And that's actually something we're going to be talking about today, or I can tie it into what we're talking about today. Anything else on your minds? Here to start. Go ahead.
Yeah. I think it should.
This is missing a wheel.
Yeah.
I might be able to do something. Oh wow, it is missing. Technically, you're missing two. Is that a little better?
Yeah, I thought I had enough in it for it.
Okay. I'll get you another one. All right. Main thing for this week is we have begun chapter 7. On Friday, we looked at some introductions to rotational motion. Rotation is going to kind of be a 2-chapter thing. Chapter 7 will be the basics of defining rotational motion, and then chapter 8 will be applied rotation, looking at specific ways it is used and specific weird cases involving it. So at least 2 weeks of rotation for chapter 7 and 8. And then after chapter 8, we're going to be heading into Thanksgiving test 2 territory. When we began chapter 7 on Friday, again just looking at the introduction to it, we started defining rotational motion, looking at how it's different but also similar to linear motion. Namely, all of the logic we've already built up for displacement, velocity, and acceleration still applies in the angular rotational world. The main differences are, instead of thinking of meters forward, we think of radians rotated. So total radians rotating over time, and the change in the rate of radians rotating over time, as well as our additional formulas, still working the same as their linear counterparts, just replacing meters with radians and English with Greek. And what we're going to be doing this week is applying some of this information to continue describing rotation and looking at various scenarios involving it. Now, today specifically, this is not meant to be a pun. I want to switch gears slightly to talk about a different application, which is centripetal force and centripetal acceleration. That'll be the main focus of lecture today, since our first rotation lab starting this week is about centripetal force. So that'll be the bulk of today, switching gears slightly from this. Any questions before we get started on that? Okay, so on screen now are 3 images that all have a few things in common. Image number 1 is someone swinging a can tied to a rope over their head, something like this. I'm going to refer back to this a few times today. The next picture is the moon orbiting the Earth, and lastly we have a bunch of cars driving in a circle. What things are in common across all of these various scenarios? One of them has tension. You said tension? Oh, sorry. Yes, there is rotation going on in all of these scenarios, but it's an interesting form of rotation. Whereas, if I hold this wheel up and spin it in place, this one object is rotating its own central axis, and it's not really moving in a straight line while that happens. These objects, though, all of them want to move linearly. They want to move in straight lines. And they would move in straight lines were it not for some specific interference in each of these cases. We know that matter wants to move in straight lines. We've talked about inertia and momentum. If something's moving, it wants to keep moving in the same direction forever. So the can, the moon, and these cars want to move in a straight line, but they're not. Why? They are moving rotationally, but they're not like orbiting their own, they're not rotating their own center axis, they're rotating around some other outside point. They are orbiting. And something is making them orbit. Because normally they want to move in a straight line. Instead, they are orbiting. And the other commonality in all these images is that there is some force making the objects orbit in each scenario. A force that is literally forcing them to do this. In the first picture, what force is causing the can to do this? Force in the string. What do we call that type of thing usually? Tension. Very good. There is a tension in this picture pulling the can towards this person's hand. Because tension always points inward, which means that on the can side of the rope, the force points towards the kid's hand. There's an inward pointing force that is making the can move in a circle like this. If that string wasn't there, the can would just take off in a straight line, right? This is how ye olde David and Goliath slingshots used to work. You'd take a rock, you'd basically put it at the end of a doubled over string, spin it around in your hand, and then let go of the rope. Because once that tension's gone, the rock just takes off in a straight line. So you just spin it until it was moving in the direction you want and then just release it. So the can wants to go in a straight line, but the tension in the string won't let it. The string's kind of acting as a leash. If you've ever seen a lawnmower tied to a rope, endlessly going in a circle, same thing. It's literally a leash. Now, what force is causing the moon to orbit the Earth? Gravity. Very different force, but it's acting in a similar way here. Rather than a literal leash, gravity is kind of acting as an invisible, metaphorical leash. There is a force between the Earth and the moon, and that force always pulls the moon towards the Earth, like how the rope, at least on this end of it, is pulling the can towards this kid's hand. So for both the can and the moon, there's a force pulling them towards the center of their orbital path. And in both cases, if that force didn't exist, the object in question would rocket away in a straight line. The moon would leave if not for the Earth's gravity, and then bad things would happen. Lastly is this scenario, and what's causing this to happen is just a little bit weirder to describe, so I'm just going to tell you. When you're driving, you drive forward because the tires point forwards and are spinning in a certain direction, and therefore they're applying a certain force to the ground. When you physically turn the steering wheel and the tires change direction, you not only change the direction that the force from the tires applies to the ground, you're also changing the direction that friction acts on the tires. So a combination of all those things changing creates a net force inward towards the center of this giant circle. And that's true anytime you turn the wheel in the car. You're changing the direction of the applied force, pointing it inward of a larger circle. And if you're just doing like a quarter turn, this might be harder to see, but technically, if you just turn left at a light in about 90 degrees usually, this is part of a giant circle. You just choose to exit the circle. You enter the circle here, and you choose to exit it here by putting the wheel back. But this is part of a larger circle. You are orbiting some fixed point, likely in a Denny's parking lot, and as long as the wheel is turned, you are orbiting because you have changed the direction of all the forces from the tire and the road. So in all these cases, the objects want to go straight, but a force is preventing them from doing that. These are all objects engaged in rotational orbit around some central point outside of themselves. Unlike the wheel, which is spinning about its own central axis, these things are orbiting around a point outside of themselves. And the presence of a force pulling them towards the center of that orbit prevents them from moving in a straight line. It creates this hybrid of linear rotational motion. They are spinning around something, but they are actually moving through linear space while they do that. Whereas the wheel, I can hold it still and it doesn't go forwards or backwards. These objects do move x and y coordinates away from where they start. So this is we're kind of starting here with a hybrid of linear and rotational motion at the same time. And it happens because in each of these cases, some different force is serving the role of what we in physics call centripetal force. You guys heard that word before today? Okay. Well, let's define that word. Hold on, my PowerPoint's programmed wrong again. So, these objects are accelerating into a circular motion. The fact that they want to move in a straight line but are not means that they are accelerating by definition. They're accelerating into a circular pattern. And this is happening because of centripetal force. Note the word I'm using. It's not the word centrifugal. I'll address what that means later. This is centripetal. Centripetal. And if you look at the root words there, centri means center and petal means seeking. So centripetal force is the center-seeking force. In all three of those cases from the previous slide, there was some force pulling the objects towards the center of an orbit outside of themselves. I'm going to redraw the Earth, or whoops, I almost said that backwards. I'm going to redraw the moon orbiting the Earth to use that as a continued example here. In this case, it is the force of gravity pulling the moon towards the Earth's center at all times. So some center-seeking centripetal force is causing the motion in each of these scenarios. That force acts upon the mass of the object, causing it to accelerate centripetally. And if an object is accelerating centripetally, it will move at a certain radius from whatever it's orbiting around based on its velocity. So an object's linear speed affects how much force is required to make it orbit at a specific radius. We'll use the formulas a bit later. In all those cases, some real force is serving the role of a centripetal force, and that centripetal force is causing centripetal acceleration. That force, the force and the acceleration, always point towards the center of the orbit. Therefore, they are constantly changing the direction of the object's motion towards the center of the orbit. So all the objects pictured in the previous slide are all accelerating, even if their speed isn't changing. This is because their direction is constantly changing. If you remember from way back in the beginning of the course, acceleration is defined as a change in velocity. Any change in velocity. And velocity, since it's a vector, is defined as both speed and direction. You can stay at the same speed and change direction, right? I wouldn't recommend doing this in a car, but you can take that left turn without hitting the brake. It's not a good idea, but you can do it, right? In that case, your speed doesn't drop, but your direction changes. That's technically an acceleration. You're slowing down in this axis and speeding up in this axis. So turning, changing direction, is an acceleration. And these rotating objects are doing nothing but changing direction constantly. Their velocities are literally every single nanosecond constantly changing direction. So centripetal forces cause centripetal acceleration. They are constantly causing the object's velocity to change direction such that they are always moving in a circle. The way that this works is, in the case of the moon orbiting the Earth, the moon, years ago when the moon was first formed, the moon was imparted with some amount of velocity, some amount of momentum. The mass of the moon wants to move in a straight line, like all objects do. And if the Earth wasn't there, the moon would just rocket through space in a straight line, like all comets and meteors tend to. However, the moon is stuck near the Earth, so there's this force of gravity pulling the moon towards the Earth. If the moon wasn't moving, what would the moon do if this force was acting on it? They just fall out of the sky, and then bad things happen. If the moon had no velocity, it would just be pulled towards the Earth, and frankly, we'd die before it even hit us. If the Earth just wasn't here, and this force of gravity wasn't here, the moon would just move through space in a straight line until it found something else to orbit. But what happens in reality is that both of these things occur at the same time. The moon tries to move forward, and Earth's gravity tries to pull it down simultaneously. We've actually studied this before. It's projectile motion. The moon moves forward and falls at the same time. So rather than ending up here or here, it does both at once. It moves forward and falls at the same time, like all those marbles we shot off the cannon, shot out of the cannon. So now it's here instead. It fell and moved forward simultaneously. Therefore, it changed direction. It accelerated. Even if its speed doesn't drop, it did change direction, it did accelerate, it didn't move in a straight line. And that's again why the centripetal force, the gravity is serving as a centripetal force, causing it to accelerate. Same is true again here. The combination of force from the engines and friction from the road causes you to keep changing direction. You want to go forward, force pulls you this way, so you end up here instead, drifting towards the center. Yes?
Does this type of force have anything to do with momentum at all?
It does. Well, the force itself doesn't, but why this works does. Because the moon has momentum. The moon wants to move in a straight line because of its own momentum. It wants to keep moving at the same speed in the same direction since momentum's a vector. And for that reason, it wants to go this way, it's being pulled this way, and that's why it did both. It accelerated down and it moved forward at the same time. The moon is only doing this because it has momentum pushing it forwards as it falls. If this wasn't here, it would just fall out of the sky. Does that answer your question?
Mm-hmm.
Okay.
What actually keeps the moon from ever getting closer to us?
Good question. I will address that today, I promise. I will address that today, because that actually ties into something that was also already asked. So I'm gonna summarize that once feel like I've given all the background information. Now, at this point, something happens. We've moved forward and fallen down at the same time, but these two vectors don't point in the same direction anymore. Because Earth's gravity always pulls towards the core of the Earth, right? That's why you always fall down no matter what part of the planet you're on. It's always towards the core. So this force of gravity doesn't pull this way, now it pulls this way. So that force has changed direction. It still points to the center of the orbit. Center seeking force, centripetal force. Not only that, but the velocity has changed direction as well, because the gravity caused the moon to accelerate. The gravity changed the direction of the velocity. So now, this points this way. Note that it's still at a right angle. Now, these are different types of vectors, but they are both vectors, and they happen to be at a right angle from one another. And that right angle has just shifted with the new trajectory. They're still at a right angle from one another. So once again, the moon wants to go here, it's being pulled in this direction, so once again, it's gonna do both at the same time and end up here rather than in either single position. And this just continues all the way around. In every single new position, force points towards the center, velocity points tangent to it, right angle to it. In every single possible position, all the way around the circle. So this combination of factors, the velocity forward and the center seeking force, keep the object orbiting at a fixed radius as long as the force and the velocity stay the same. So the gravity is always pointing towards the center of the circle. That's why we call it a center seeking force, a centripetal force, causing centripetal acceleration to cause the object to constantly keep changing direction. Any force can actually act as a centripetal force. It doesn't have to be gravity, because one of the other cases on the previous slide was someone just doing this. Here, it's the tension in the rope serving as a centripetal force. And it's keeping this rubber plunger cork thing moving at a certain speed, at a certain radius from my hand. If either variable changes, force or velocity, then the whole thing changes. Or radius. If any of the three things change, then the rest of the system changes with it. Any force can serve the part of a centripetal force. Unlike other forces where, gravity always pulls us towards Earth's center, things like that. Unlike other forces that always have their specific scenarios and their specific uses, centripetal force is kind of vague in that any other force can serve the part of centripetal force. It's like a role in a play, and some actor has to be cast in that role. For the moon, gravity is cast in that. For that rotating plunger thing, it's tension in the string that's doing it. So some real force always has to serve as the centripetal force. And it's going to be different in any given scenario, but admittedly, gravity and tension are going to be the most common too. If there's a rope involved, it's probably tension. If something's orbiting in space, it's probably gravity. But either way, whatever force is doing it could change from any given question to question. Questions so far? Okay, now, two students at this point have indirectly asked about why the moon doesn't get any closer to the planet, or similar question, are planets drifting towards the things they orbit? because technically the same thing is happening as the Earth orbits the sun. This happens whenever anything orbits anything else in space. Moon around Earth, Earth around sun, Pluto around sun, sun around galactic center, things like that. All orbits, this sort of thing happens. And for this to keep happening, every single one of these variables has to remain the same. The moon's mass has to be moving at a specific velocity, at a specific distance away, and a specific force has to be acting to cause that. They all have to be totally balanced. And this situation only stays the same if they're totally balanced. Now, the moon wants to move at the same speed. Its own momentum and inertia take care of that. But inevitably, since space isn't totally frictionless, there is technically a teeny tiny amount of mostly negligible air, but it's not a perfect vacuum, and there's always weird forces from other nearby objects, because technically Pluto's exerting gravity on you, which is really weak. But there are weird extraneous forces on the moon that cause it to shift around slightly. And over time, the moon is going to slow down. And the most common thing that would happen if the moon slowed down, I'm going to kind of show it here. If I'm spinning this at a certain constant speed, and I allow it to slow, it technically gets closer and closer to my hand, just in terms of the x-axis. Y-axis, it does fall down, but x-axis, it drifts closer to my hand as it slows down, right? Because as the speed drops, radius would have to drop with it if the force stayed the same. And we can't really change the force of gravity acting on the moon. That's going to stay constant. So if its speed drops, its orbital radius drops. And that means the moon will fall out of the sky as it gets slower and slower. And technically the same thing happens with anything orbiting anything in space. So as friction and weird environmental space forces cause all objects to eventually slow down, they will all drift closer and closer to whatever they're orbiting. Moon closer to Earth, Earth closer to sun. Both of those things are bad. Does that answer the relevant questions that were asked earlier? Now, if the moon ever did measurably slow down, Earth scientists would probably pull together to try to figure out a way to speed it back up, which would probably involve spending all of our money to install rockets on the moon. That might not even work, if I'm being honest. That's a very Futurama answer. But we have to go through that pretty often with the space station, if I'm being honest. The space station orbits a lot closer to the Earth, and this is not a scale drawing, but if I was to try to make it scale, the space station would be right about here. It is not very far away. And the same thing happens to it. It constantly slows down because of friction and other space forces that you can't always account for. And to keep it from falling out of the sky, they have to fire the thrusters every so often to keep its orbit from decaying. Same is true of most satellites, actually. They need ways to stay in the sky, or else they just fall and burn up, and then you don't get your $1 million back. We've lost a few satellites because their thrusters broke and they just fell out of the sky.
Do they just continue to fall?
They will fall, but when they hit the atmosphere, the air friction will incinerate them. So they will keep falling until they cease to exist or hit the surface, whichever happens first. The question. Okay. Loads of things actually just incinerate in the atmosphere. Way more meteors than you realize approach Earth. They're just so small that they are incinerated before they hit the ground. All right. How do we feel with the concept of centripetal force and the acceleration that it causes? Okay. Now, we've got some formulas here. I actually want to, I'm going to change my intended order slightly. Let's use those formulas in a quick sample question before I give one more. I'm getting ahead of myself. Let's use these in a quick sample question. We're gonna put numbers to can, orbiting, hand, or when I do this thing, we're gonna put numbers to that. We're gonna have a 1 kilogram rock tied to a 1 meter rope, and we are gonna spin it over our heads at a linear speed of 3 meters per second. So, mass, 1 kilogram, orbital radius, 1 meter, linear velocity, 3 meters per second. That's the speed that it wants to move at if there wasn't a rope forcing it to move into a circle. First question, what must the centripetal acceleration acting on this object be to cause it to do this? Bless you. The new formula for centripetal acceleration is going to be v squared over r, or alternatively, omega squared times r. So on your formula sheet, English A, this isn't alpha actually, this is English A. English A with a subscript C, this stands for acceleration centripetal, is equal to linear speed squared over r, alternatively, omega squared times r. These both give you the same answer. Since the object is technically moving in a circle, you could describe its motion as either this is its linear speed moving in a circle at this radius, but since it's in a circle, you could also describe its motion as a rotational speed. So whichever version of the formula just kind of depends on which variable you know. You know, linear speed in meters per second or rate of rotation in radians per second. Either way, you can get to AC from that number, whichever one you happen to have. Interesting correlation. The moon's linear speed is very fast. It's moving many times the speed of sound through space. But its rotational speed is actually very slow because it takes it a whole day to do just one lap. Now, in this case, we have a slow object and a very low mass, so smaller numbers here. We know the linear speed of the rock, so we'll just use 3 squared over an orbital radius of 1. The length of the string would just be the distance between your hand and the stone. We call that radius because it forms the radius of the larger circle. So the centripetal acceleration of the stone would be 9 meters per second squared. This doesn't really tell you how much the velocity, how much the speed changes with time. This tells you how much its direction changes with time. The bigger the centripetal acceleration, the more force is required to pull it into a circle, the more its direction changes with time. Any issues finding this one? All right, now we're going to use that number. What must the tension in the rope be to make this happen? 9 newtons, you're right. Now, to show where that number comes from, what is tension in the rope doing in this scenario? It is going to act as the centripetal force. So in this case, tension is the actor that has been cast in that role. So if we find centripetal force, we find tension. Because the tension in the rope is what is causing the rock to do this. If the rock wasn't there, it wouldn't be moving, if the rope wasn't there, the rock wouldn't do this. It would just fly away in a straight line. So tension is serving as the centripetal force, causing the rock to move in a circle. So if we find centripetal force, we find tension. And centripetal force is equal to mass times centripetal acceleration. It's a variation of Newton's second law. So 1 kilogram times 9 meters per second squared. 9 newtons of tension in the rope to make this happen. Conveniently used meters, normal meters per second and normal kilograms to make this one a little quicker. This means that if the rope can't bear 9 newtons of tension, it would snap and the rock would just fly away in a straight line. This is the sort of math that you have to do if you are David trying to attack Goliath. There was a lot of force involved in that swing, and the sling needed to be able to handle it. If it doesn't, it breaks, and everything just stops working. Questions finding that number? And make sure to bring these notes to lab, because lab this week is going to involve centripetal force. Namely, you are going to be spinning an object tied to a rope. Therefore, once again, the tension in the rope will act as centripetal force to make that happen. So, once again, this is what lab this week is about. While I've got the numbers on screen, what would happen if the rock sped up? What would happen if you just chose to swing it around faster? Velocity would change. Well, yeah, velocity would change, definitely. If you chose to spin it faster, this number would change. And I'm actually going to try to demonstrate it with this thing. What's neat about this particular tool is that the other end of the rope is actually tied to a force gauge. So you should be able to ideally see the dial turn if the force involved changes at all. So first I'm going to spin nice and slow. Note about how much tension is required in the string to make that happen. Now I'm going to speed it up. Anything change? Force go up or down? Okay, it kind of lapped back around to 0. Sorry. So right now it's averaging about 3 newtons, right about here. When I speed it up, it maxed out. It scaled back around to the starting position. I'm going to show that. I've got it pulled all the way out and show it loop back to 0. So it was here, then it maxed out. Increasing the velocity, if 3 was, say, 4 instead, would increase centripetal acceleration if the radius stays the same, and that would increase the amount of force required. This is why it would be bad if the moon somehow sped up. It would need more gravity to stay in place, and since we can't really adjust that gravity, that would actually naturally cause the object to try to drift further away. If things slow down, they fall closer. If things speed up, they run away. So we want the moon's velocity to stay exactly as it is. We don't want it to decay or get faster. Not that it would ever spontaneously speed up for any conceivable reason. But I'm bringing this up to kind of show that there's a very delicate balance between all 3 of these things. If any one of these changes, the whole situation could fall apart. If the velocity increased, the amount of force required increased, and therefore the tension in the rope increases. And if the tension can't bear that force, it snaps. You can also just manually change the radius to change things as well. Because if I try to spin at constant speed and I just make the rope shorter, force goes up and velocity goes with it. They're all balanced. It takes a very specific combination of variables to make any object orbit at any speed and at any given radius. If any one of those changes, the whole system could fall apart. And that's why our entire solar system is very precariously and finely tuned. Precariously balanced and finely tuned. questions thus far? All right. Now, last thing I want to talk about today, I'm going to tap back a second. I've been saying centripetal very purposefully today, because there's another word that you might have heard that I'm very specifically not using. Especially if you hang out upstairs and use centrifuges often enough. You've probably heard of centrifugal force. Does that sound possibly more familiar? Okay, mixed reactions. I want to bring it up before we break for the day to kind of dispel any possible confusion before it starts. Centrifugal force is a different concept to centripetal force. They are similar words and similar concepts, but they are different. Centripetal means center seeking. Petal means seeking. Centrifugal means center fleeing. So the centrifugal force is this notion that when you're spinning in a circle, something is trying to pull you out of it, pull you out of that circular motion. Where you might have felt this before is if you're riding in a car, and I don't recommend doing this, but say while in that car, the driver, be it you or someone else, realizes all of a sudden, oh crud, I have to turn now, and they crank the steering wheel, and the car starts turning really fast at speed. Here, from above, we've got to turn to the left. If that were to happen, and again, wheel cranks this way, car very suddenly starts turning left, what do you feel happen to you while the car does that if you're in the car? I'm going to turn around and try to show the perspective. Wheel turns left, and does it kind of feel like this happens? That's something you felt at some point in your life, either in a car or on playground equipment. That feeling is the centrifugal force. It kind of feels like as the car moves to the left, something's pulling you to the right. It could almost pull you out of the car completely if you weren't wearing a seatbelt. Wear a seatbelt for that. That's what the term centrifugal force refers to. The centripetal force is what is actually pulling you towards the center of the orbit along with the car. The centrifugal force is that feeling that something could pull you out of the circle at any minute. And the quirk about centrifugal force is that it isn't real. Not to argue with the fact that you're feeling something. You are feeling something. I'm not arguing with your sensory perception. I'm arguing that there is not actually a force pulling you out of the circle. There isn't actually a centrifugal force to calculate, and that's why the formula is only for centripetal force. We are only going to acknowledge centripetal force in this class because it's the only one of the two that is a real number that can be calculated. Centrifugal force, I need to change the background of the slide. This last blurb was too hard to read, sorry. Centrifugal force isn't a real force, it's just a sensory phenomenon. I will elaborate. When the car drifts to the left, you are a separate object from the car, correct? You are not your car. So when the car turns left, your own momentum and inertia tells your own body, hey, that's boring, keep moving in a straight line. Because everything wants to move in a straight line, right? So your body wants to move in a straight line even as the car under you turns left. And what happens is, wear your seatbelt, as long as you are stuck to the seat of the car forces you to the left. However, just like you're not a part of your car, your body is also not one single object. You're a bunch of different objects all stapled together. Limbs and blood and organs and all that. So if your torso is seatbelted in and your torso gets pulled to the left, well, your head and your arms have their own inertia telling them keep moving in a straight line anyway. So as the car turns to the left, your own inertia tries to get you to move in a straight line, which feels rightward based on your ever-changing leftward-facing perception. If the car is yanking you to the left, it feels as if your body wants to move to the right, when technically it wants to move in a straight line. Your own body's momentum wants you to do this, and so that's why, your torso and any unused arms tend to fly in that direction. But there's not actually a force causing you to do that. It's just your own momentum saying move in a straight line as the rest of you gets pulled to the left. So it just kind of feels rightward. And there isn't a force making you do that. It's just your own momentum. It might feel like there's a force doing that. And that is, again, because your body is not one single object. Your blood has its own momentum, which is where dizziness comes from. When this happens, it's not just your limbs that try to go away from you. Your own blood tries to do it too. And so your blood ends up pressing against the outer wall of your body, exerting what feels like a rightward pointing force. If my body's being pulled this way and my blood tries to move this way, it feels like my blood is kind of pushing to the right from inside of you. It's an internal force, so it's not really doing anything to you. And likewise, your skin is just going to physically pull the blood to the left along with the rest of you. But you get this weird feeling of this rightward force that isn't really even there. It's entirely a human sensory phenomenon. So centrifugal force is called fictional because there just isn't an actual force involved. And since there's no force to measure or calculate, we don't use it in this class. So that is why the word centrifugal force will never come up in our math. Only centripetal force, which is a measurable actual force that we can calculate. Centrifugal force is a sensory phenomenon that you have felt, but cannot be qualitated. Does that make sense? Does that feel okay? And you can feel this force even if you just swing your own arm around a lot, because eventually your blood will rush to your fingertips. And centrifuges, the machines upstairs that you guys probably use, they are based on this phenomenon, because kind of like how your blood will rush to your fingertips, all the particulates in whatever you're centrifuging rush to the edge of the test tube. But still, that is all because of centripetal force, not because this is not a real force that does it. It all ties back to this force instead. So this last 10 minutes have just been me diatribing about this phenomenon. Questions, concerns, anything at all on your minds? All right, once again, bring these notes to lab whenever you have that. Let me know if you guys need anything. Have a great day.